let's meet today's speaker. We are joined by Steve Aubuchon, and Steve is a market and business development lead for W.L. Gore and Associates, focused primarily on the electronics and battery markets. He joined Gore in 2017 with an extensive background in business leadership, product management, and technical sales in the laboratory instrumentation market with TA Waters Instruments. And with that, I'd love to hand the stage over to Steve.
Thank you, Michael. I'm going to share my screen now. Okay. So again, thank you for that introduction, Michael. We're very happy to be here today, especially given the technical difficulties that we had on Tuesday. We're happy to see so many participants and very excited to be able to share this new technology from Gore for stable thermal barriers for safe high-density battery systems. So during the presentation part, I'm going to go off camera, but then at the end, we'll put my camera back on as we get to the Q&A. So as I mentioned, we're happy today to talk about this new technology that we're developing here at Gore, specifically for battery energy systems and to provide stable thermal barriers to make these battery energy systems safe and higher density. But before I get started, I'd like to just give a little bit of introduction to myself. As Michael mentioned, my name is Steve Aubuchon. I'm the market and business development lead for the electronics and battery systems here at Gore. I have a PhD in inorganic chemistry, electronic materials chemistry from Duke University, and I do hold a BS in chemistry from St. Louis University. In addition to my work at Gore, I'm also active at the University of Delaware, where I'm an affiliated professor in materials science and engineering, and I also act as a mentor for the University of Delaware Horn Entrepreneurship Program. So with that, let's talk a little bit about the agenda for today. I'm going to go through a few slides just to give an introduction to Gore. We'll then review the concept of thermal barriers and the jobs that thermal barriers provide to battery modules. And then we'll introduce the new technology, which we refer to as GORE Battery Insulation, or GBI. We'll consider the effect of compressibility on insulations and specifically on thermal resistance, because thermal resistance is a key quality of any insulation, and we need to understand how compressibility can potentially affect that. We'll then give a comparison of the Gore battery insulation technology to alternative materials, which are often used as insulation materials, and provide some real-world examples. So let me start with an introduction to Gore. Gore is an advanced material science company, and we started this business with PTFE. And the ability to expand PTFE from a dense form to a more open, porous structure really created tremendous valuable characteristics and the ability to combine with a variety of other materials. So in the decades that followed that initial introduction, we've built on that core understanding really across a focused set of materials, which allow the creations of literally thousands of products that solve complex problems with our partners. Now, the vast majority of Gore products are not just pure polymers, but they are composites. And they're made up of expanded polymer intermediates and other dissimilar materials and proprietary adhesives that perform in very demanding environments, from the human body to the moon even, and back. Now today, Gore is a community of about 13,000 associates, and we're spread globally. We have manufacturing facilities around the world, here in the United States, various countries in Europe, as well as in Asia, in Japan, and China. We're slightly more than $5 billion in annual revenue, which makes us one of the 200 largest privately held U.S. companies. We're not a public company. We're a private company with ownership through our associates. We hold a portfolio of over 3,000 unique inventions. And one thing that's really unique about Gore is our culture. We're recognized globally for our culture and fostering a work environment that gives our associates the freedom to grow. We have a long history of really leveraging that freedom to grow, and that has helped us to maintain our reputation as a great place to work. But it's not just the associates that grow. Gore also grew over the years from a wire and cable business to being active in over 15 diverse industries. And we connect with our customers and partners across a wide range of industries. You might be familiar with our probably our most popular customer-facing brand of Gore-Tex, which is in apparels and textiles. But Gore is a much bigger company than that, and we're active in medical, life sciences, aerospace defense, automotive, semiconductor, and especially here in electronics and clean energy applications. And our businesses test their products extensively in laboratories under real world conditions. And we're going to show you some examples of that as we introduce the thermal barrier material, GORE Battery Insulation. So with that in mind, let's dive into the problem. The problem that we've identified is thermal runaway propagation. And while lithium-ion battery technology absolutely offers many benefits, the rare but possible thermal runaway event must be acknowledged and especially managed. And one of the reasons for this is because when thermal runaways occur, they make the news. And I'm sure that most of you have heard of the Moss Landing fire that happened out near Monterey Bay, California, back in January. It was a fire that started and burned for several days. It was on the news, it was on the national news. Granted, this was an older installation, which likely didn't have many of the modern safety uh, features, but it still represented a tremendous peril to both the facility as well as those around it. And even more recently, if you know just Google for battery fires, you can find a lot of stories that hit the news, such as this story from later in July about battery-powered construction equipment leading to evacuations. And so these things get a lot of press and a lot of coverage. And so it's critically important to address the risk of thermal runaway propagation, of course, because of the safety to users and first responders and the financial losses that can occur. But the plume of gas that comes off of lithium-ion batteries when they're in thermal runaway is, of course, an environmental hazard and can result in collateral damage to not only the installation but adjacent structures. But often what we don't think about is the reputational damage as well. We're all involved in the battery industry, and we want the battery industry to be viewed as safe and durable and reliable. And anytime one of these incidents occurs, it absolutely tarnishes the brand, not just from the owner of the battery, but everyone involved, including the lithium-ion battery ecosystem in general. And so we feel it's critically important to manage the risk of thermal runaway propagation. So to that end, we deploy thermal barriers. And thermal barriers are designed to mitigate cell-to-cell thermal propagation, as shown here in this little schematic diagram. Imagine that you have an array of prismatic battery cells, shown here, and in between, we often deploy thermal barrier layers specifically designed to mitigate propagation. And the typical solutions that are used are aerogels, sometimes cork, and very often silicones or polymer foams. And these solutions are very, very uh, good at mitigating thermal propagation. That is exactly the first job that they're hired to do, which is to manage the thermal risk and mitigate that thermal propagation. But the downside comes in energy density. Any place that you're putting a thermal barrier, you're not putting active material. And active material, of course, is what increases energy density and allows for the valorization of these types of installations. And so for that reason, it's desirable to use the thinnest thermal barrier layer possible so that we can maintain that high degree of safety while at the same time helping to optimize the module energy density. Now, in addition to providing that thermal protection, these thermal barrier layers are often also expected to be compliant layers because as the installation is charged and discharged, and even as the installation ages, there's going to be a volumetric change in these batteries, and they're going to swell and both in a linear fashion as well as in a cyclic fashion upon charging and discharging. And so the compliant layer is necessary to help manage that swelling and to help pick up a lot of the compressive stresses that can occur as these batteries age and as they're charged and discharged. Now, our suggestion is that the asking the single material to do both of these jobs, to mitigate the thermal propagation as well as to introduce the compliant layer, is somewhat difficult because these two jobs are actually counterproductive to each other, as we'll demonstrate in some of these subsequent slides. It all comes from the concept of thermal resistance. Thermal conductivity is an intrinsic property, and it's often used to describe the performance of a thermal barrier material. And thermal conductivity absolutely describes how well a material conducts heat. However, thermal resistance is a more appropriate term to reflect how effectively a thermal barrier resists heat flow. And so when we're talking about thermal barrier materials, we suggest that thermal resistance matters more than thermal conductivity. So thermal resistance can be defined here by this equation. It's often called the R value of insulation, and it's simply the thickness of the barrier layer divided by the thermal conductivity. So thermal conductivity is absolutely a component of this, but it also takes into account the geometry of the material, or the thickness. So imagine that you have a pair of cells and you're going to place a thermal barrier material between them. That thermal barrier has a thermal conductivity of K, which again is an intrinsic property. It's not a function of the dimension, but it also has the value of L, which is the thickness. Now imagine that you apply some compression. And so if the thermal barrier layer is compressible, then that value of L is going to decrease, which means that upon applying compression, the K value will often remain constant. However, the R value, the thermal resistance, will decrease in conjunction with the decrease in thickness. So in real-world environments, maintaining a consistent R value under these compressive stresses, that is what defines thermal protection, not just low thermal conductivity, because the thermal barrier performance can absolutely be detrimentally affected under compression. And this is the problem that we set out to address with GORE battery insulation. So at this point, I'd like to introduce the concept of GORE battery insulation technology, and I'm going to play a short video here which explains what GORE battery insulation is and introduces some of the benefits and the differentiation of this. This video also features my colleague, Kelly Hillen, who is the lead new product development engineer on this technology.
One of the biggest concerns about battery installations is safety, specifically safety from thermal runaway. In battery modules, there are really two jobs which need to be done. First, thermal barrier. You need to protect against thermal runaway propagation. But also, you do need to have some sort of compliant material so that you can take up the compressive stresses that the batteries are put under.
When a lot of gas is generated in the cell, that applies a lot of compressive stress on the insulation material between the cells. So in this critical moment when you need the insulation to be really robust and providing that protection against thermal propagation, a compressible thermal barrier will be compromised.
GORE battery insulation is an incompressible thermal barrier, which means it's going to retain its thermal properties even under compression. And it can be then paired with a compliant layer in alternate cells so that you're taking care of both jobs, the thermal barrier job and the compliant pad job, and you're doing both of them better. GORE battery insulation is a much easier to handle material than traditional battery insulations. It's delivered in a form that is cuttable, it's bendable, and it's non-shedding and non-particulating. So it can be bonded using adhesives, it can be layered with other materials, and it's very easy to handle. And in this growing field, this is something that we're very excited about. We've been talking to a lot of customers, and we understand the problem to be solved, and that is to improve the safety of grid-scale battery energy storage. And GORE battery insulation will be very well positioned to help our customers improve the safety of their battery storage installations.
Okay, that was a quick introduction to GORE battery insulation, but let's take a little bit of a deeper dive. So again, GORE battery insulation is a technology which is specifically intended to boost energy density while still providing that thermal barrier layer and a durable thermal propagation protection. We start with a very low thermal conductivity material, especially at elevated temperature, but then we've engineered it to be stable under pressure. And we're going to show some specific examples of this. As shown here in the video, we can produce this in tape form to very high precision, to within plus or minus 100 microns of variability. And as also shown, it's bondable. It can be adhered using adhesives. It's flexible, bendable, and it is very, very low particulation. If you see here in the video, at one point, we're scraping the material with a razor blade, and very little particulates come off. And so it's basically made for manufacturing. And GORE battery insulation then provides a more durable thermal barrier under the extreme conditions of compression and high temperature based on all of these properties. So let's take a look now at the performance. Now, as this material is a technology, it's not yet commercialized. We intend to commercialize GORE battery insulation in the early part of 2026. So all of this data is still preliminary and potentially could vary with configuration composition, but this is the performance that we're expecting. Thermal conductivity at 100 degrees is less than 45 milliwatts per meter Kelvin, and that value does not change much as we go to 500 C. It rises only about 10%. As we mentioned, we can produce this in tape form nominally at 1 millimeter, but we can have discussions about producing in thicknesses less than a millimeter. Dimensional tolerances are very tight at plus or minus 5%. Very low density material, less than about 0.4 grams per cc. And as I mentioned, the differentiation between GORE battery insulation and other materials is in its performance under pressure, under compressive stress. So the compressive strain at 1 megapascal of stress is less than 5%. And we're going to dive into this in the subsequent slides. It does carry a flammability rating, UL94HB, and we are able to offer this material with a country of origin here in the United States. We recognize that with the Big Beautiful Bill and the ITC and the various regulations that having a COO from the United States is very important for those manufacturers here in the United States. And so we can offer this material with a COO here from the United States. So let's think a little bit about compressibility. And first of all, how we measure compressibility, and secondly, its impact on the thermal barrier performance. As I've mentioned, GORE battery insulation exhibits very low strain, even at high pressures. And that can be seen here in the stress strain plot on the right side. In this case, we're comparing GORE battery insulation, which is the red line, to two different commercial aerogel pads, which are marketed as battery insulations. We're just going to refer to them as Aerogel A and Aerogel B. And all of these materials are measured with an initial thickness of 1 millimeter. So you notice as we begin to put compressive stress on the material, the aerogels, being compressible materials, show significant strain. In the case of Aerogel A, up to about 35% decrease in thickness. And with the more compressible Aerogel B, we're at about 55% decrease in thickness. So we're going to be starting with 1 millimeter and decreasing. Compare that to the GORE battery insulation, where we're starting at 1 millimeter, applying that same amount of stress, and you see that the compressive strain is less than 5%. So that means that the thickness value is not going to vary with compressive stress, and that in turn means that the thermal resistance is going to remain constant and durable during this entire condition. So we can test this, but let's first understand, the impact on energy density under a variety of different conditions. So imagine that we're starting with two different battery modules, one of which is protected with GORE battery insulation at 2 millimeters, and the second with an aerogel-based battery insulation starting with 4 millimeters. Now, the reason that the aerogel insulation is thicker is because with aerogel, you have to consider the compressible nature. And so with zero compression load, just at manufacturing, often you must install a thicker layer to account for the inevitable compressibility. So now in the case of GORE battery insulation, if we apply a fairly modest compression of about 50 kilopascals, we don't expect to see any compression at all. So that initial 2 millimeters will remain 2 millimeters under the manufacturing stresses of about 50 kilopascal. But now imagine that this battery cell on the right were to go into thermal runaway. And when thermal runaway occurs, gases are produced inside the cell, which cause the cell to rapidly swell and to apply a much higher compressive stress on the barrier material. So imagine now under 1 megapascal of compressive stress, when the battery cell's in thermal runaway, GORE battery insulation is expected to maintain to within about 100 microns of that initial 2 millimeter thickness, and that is simply due to the low compressibility. Now let's compare that to what we might expect under the same conditions with an aerogel-based battery insulation. So again, imagine that we're starting with 4 millimeters, and we're going to apply just a modest 50 kilopascals of stress. Under that 50 kilopascals of stress, based on the stress strain curve, you might expect about 10% compression. So your initial 4 millimeter layer is now down to 3.6 millimeters. Now imagine that, again, the cell on the right goes into thermal runaway and produces a megapascal of stress. So under these conditions, the aerogel-based insulation is expected to compress even more, all the way down to 1.6 millimeters from that initial 4. Remember that the thermal resistance is the thickness divided by the thermal conductivity. The thermal conductivity is staying roughly the same, but the thickness has decreased by about 60%. And so with the thermal resistance dropping by that 60%, now we have a pathway for heat to flow and potentially to begin affecting the neighboring cell. And that is, of course, thermal runaway propagation, and that's what we're trying to guard against. So this is a theoretical model of what could potentially happen. Now let's look at actual data that's been collected in the lab. So in our experiment, we've done basically a modified hot side, cold side test. On one side, we have a heat source, which we refer to as the trigger cell, and we're going to heat this to 800 degrees Celsius. We're then going to rapidly squeeze a layer of thermal barrier candidate, whether it be the GORE battery insulation or an alternative material, between the hot side, the trigger cell, and a cold side, the adjacent cell. And that cold side is initially maintained at ambient temperature. Now, ideally, the hot side should stay hot and the cold side should stay cold. But the direct measurement of the impact of the thermal barrier material will be on the peak temperature that is achieved during this experiment. So we're going to take thermocouples on both the hot side and the cold side, and we're going to measure the temperature decay over the duration of about 15 minutes. Now, our test rig also has the ability to vary the amount of pressure that we're applying. So we can apply modest pressure of about 50 kilopascals, and we can discretely increase that pressure in subsequent experiments to see how the pressure affects the backside peak temperature. Keep in mind that ideally the cold side temperature should stay below about 150 C, because above 150 C is where changes begin happening to separator materials inside lithium-ion batteries, and that's where additional breakdowns can occur. So 150 C should be kind of the target in terms of keeping the cold side cold. Now we're going to plot our data over here on the right. And in this plot, we have on the x-axis the applied pressure. Remember, this is discrete points in multiple experiments. And then we're going to compare that to the peak temperature over here on the left side. And ideally, at all of these pressures, the peak temperature should remain below 150 C. All of the materials that I'm going to show were tested at an initial 2 millimeter thickness. So let's start with aerogel A. You see that initially, under modest compressive stress, we do maintain a fairly low temperature, peak temperature of about 135 degrees. But as soon as the compression is increased and the stress is increased, you see that very quickly we jump above 150, and in fact, at 500 kilopascal, we're up to almost 195 degrees C. So this would be a non-ideal condition. Compare that to the aerogel B material. Again, we're starting out fairly low under modest pressure, but once we get to 500 kilopascals, now we're well above 150, almost 165 degrees C. So now let's compare this to the performance of GORE battery insulation. GORE battery insulation starts out with an initial very low temperature, again in the same ballpark as the aerogels, but you see even under conditions of increasing stress, it maintains that durable thermal barrier. It's maintaining its R value, its thermal resistance, so that even under 500 kilopascals of stress, we can maintain a peak temperature well below 150 degrees. And this is ideal for the performance of a thermal barrier material. So it's offering a more durable thermal resistance and thermal barrier properties under extreme conditions of high temperature, as well as high compressive stress. So we can measure this in the lab, and we can also measure it in real time. But what you might be thinking at this point is, what about compliance? Because as I mentioned in one of the earlier slides, compliance is necessary to manage battery swelling. And if the GORE battery insulation is a low compressible material, how can we manage that second job? Well, it's pretty simple. And what some of our testing partners have done is to simply replace some of the thermal barrier layers in the module with compliant layers. And these compliant layers can be very low cost materials specifically designed as compression pads. And so in essence, what we're doing is we're separating the jobs and doing both of them better. Now, this is not the only strategy to introduce compliant layers. We're also investigating the potential for making heterogeneous laminates, which would include a thin layer of GORE battery insulation laminated directly to a compliant layer or a compression pad layer. And with that in mind, we have a variety of different options to again address both jobs, separate them, and do them both better. But this first example of putting compliant layers in alternate junctions has actually been tested in the field in a mini module test by one of our early testing partners. And here's the schematic for that experiment. In this experiment, we have 18 prismatic cells, 2 rows of 9, and the center cell, shown here by number 16, is going to be put into thermal runaway. We have protective materials, thermal barrier materials, in the gaps every third cell. So here at the number between number 4 and 5, and again between number 10 and 11, we're going to have a thermal barrier material. And the alternate junctions, the uninsulated junctions, are fit with simple compliant pads. Everywhere you see a number, we're going to make a temperature measurement, a thermocouple measurement, so we can determine what are the maximum temperatures that this battery module is experiencing when we put the center cell, number 16, into thermal runaway. So here are the results. First, with an alternative material of cork. And the cork insulation was actually deployed at about a 50% thicker layer than what we're going to compare to GORE battery insulation. So as they say, a picture tells 1,000 words. As you can see here, the center cell was placed into thermal runaway. That thermal runaway propagated, of course, to the cells on the left and the right, but it then also jumped over the thermal barrier layer and was able to propagate all the way to the end of the module. In addition to the visual evidence, the thermocouples also show that even the most remote thermocouples are well above 150 degrees C, in some cases approaching and even exceeding 300 degrees C. So this is a non-ideal result from this thermal runaway propagation test. Now let's compare it to the same exact test, same exact type of battery module, but now protected with GORE battery insulation. And you can see the results are pretty striking. Again, the center cell is the one placed into thermal runaway. It propagated just to the neighboring cells, but where the thermal barrier layer GORE battery insulation was deployed, we saw no additional propagation. So in essence, the GORE battery insulation was able to contain the thermal propagation just to the cells that were between the two layers. And in fact, if we look at now the thermocouple measurements, you see that the most remote thermocouples barely moved above ambient and didn't approach anything close to 150 degrees C. And then the closer thermocouples to those cells, really only achieved slightly above 100 C. So these photos and this data were provided by one of our early testing partners, which is Our Next Energy. And based on the results from these experiments, Our Next Energy has provided several conclusions. And their conclusions are as follows: that the GORE battery insulation outperformed alternative insulations such as aerogels and silicon foam-based solutions, especially at a practical thickness and cost. And remember, thickness is what leads to energy density. Secondly, that the GBI material demonstrated a limited change in thermal conductivity, especially at higher temperatures. Its relative incompressibility resisted the violent cell swelling that occurred during thermal runaway. And finally, that GBI represented the best solution which met the customer trade-offs of cost, size, and thermal propagation performance. So I'd like to now come to my conclusions. GORE battery insulation, again, is a technology which is designed to boost energy density while preventing thermal propagation. Our initial target market is stationary BESS, but we are absolutely interested in exploring deploying this material in any application, including automotive, EV, aerospace and defense, adjacent markets, e-mobility, power tools. We believe that it has a tremendous value in a range of applications, and that's based on its ability to increase energy density. It offers a higher thermal resistance, especially at a lower thickness, and it is dimensionally stable under extreme compression load, and that provides a consistent and durable protection. As you've shown in the video, it's very low particulating, it's cuttable, it's bondable, very flexible. So in essence, it's made for manufacturing. And finally, as I mentioned, it can contain or carry the country of origin from the United States. It is a non-fluorinated material as well. So this is all intended to help support compliance, sustainability, and of course, those important domestic content goals. I should also mention that there is absolutely no foreign entity of concern in there. There's no FEOC concerns whatsoever with the GORE battery insulation. So with that, I'm going to conclude my prepared remarks, but I will mention that we are absolutely interested in talking with OEMs and engineers who can help us test and validate GORE battery insulation. It is still a pre-commercial technology. We're intending to commercialize in early 2026. So we're looking for partners. We're looking for OEMs who are interested in sampling the material and testing it and investigating deploying in a variety of applications. So as an early partner, you could get a close look at this next standard in battery safety and help influence the technology even before it hits the market. So I've put up two different QR codes here. The one on the left will take you directly to the GORE Battery Innovation page, which has more information about the GORE battery insulation as well as some other technology which we're developing. And there is a form on there that you can fill out if you'd like to contact us. Or if you prefer to just contact me directly, you can use the QR code on the right. And if you scan this with your phone, it should open up a contact page that has my name, my email address, my phone number, and my LinkedIn account. And I would encourage you to reach out to me if you're interested in participating in studying GORE battery insulation. So with that in mind, I'm going to conclude. I'm going to come back onto camera, and I'm happy to take any questions that you might have.
Perfect. Steve, that was super interesting even for the second time. So I'm glad that we got through this. Just as a quick reminder for everybody who's interested in asking questions, at the bottom of your screen, a little bit right to the green share button, you'll see a Q&A button where you can ask questions we'll be able to answer. Just also want to highlight for those who are interested in more information, there are also documents within the resources tab of this presentation. So if you click on the resources button, there should be 3 documents, including a white paper, brochure, and also some more information from the GORE team. Now, as we're at the Q&A portion of this event, I'll be asking some questions that y'all have posed in the chat. Matthias has asked, what is the material family of the GORE thermal barrier?
Good question. So as I mentioned in the early slide, most of the materials that GORE produces are composite materials. And GORE battery insulation is also a composite material. It has a polymeric base, but it's primarily the thermal performance is primarily based on an inorganic cocktail of materials. One of the capabilities here at GORE is that we have a lot of deep knowledge about how to fill polymeric substrates and polymeric matrices with functional materials. And so that is basically what GORE battery insulation is it's a small amount of polymer used as a matrix and binder, and then it has a proprietary inorganic cocktail that will help to resist both conductive as well as radiative heat flow.
Got it. So it's a composite material. Awesome.
Mhm.
Um, Nick Kamara asked, what is the plant cost of the Gore material and how does it compare to traditional aerogels?
Mhm. So, good question. And as I mentioned, we're still in the development phase here. We're scaling this material and we're still developing our supply chain. And so, we don't know exactly what the cost is going to be, but we recognize that in order for this material to be successful, it needs to be cost competitive with other materials that are on the market. And so if you recall the statement from Our Next Energy, that they believe that the material was the best performer based on system cost. And so the cost will absolutely depend on the customer's application, things like the material use, the volumes, but we absolutely intend for this to be very cost competitive with alternative materials on the market.
Perfect. Thank you. Phil Gao, by the way, hi Phil, asked, what is the density of this material and what are common thicknesses you can provide for this?
So the density is slightly less than 0.4 grams per cc, grams per milliliter. So it's a very low density material. And in terms of thicknesses, we intend to produce this nominally at 1 millimeter thickness. We find that that is a pretty good starting point for most applications. If thickness is greater than that or required, you can layer various materials together. We also have the ability to produce at slightly lower thicknesses, down to about 500 microns, but ideally we would offer this material at 1 millimeter thicknesses initially. That's our nominal thickness, but we're happy to have discussions with interested customers if variable thicknesses are interesting.
Perfect. Sounds good. Um, Pavel Banik asked if you could go back to the experiment thermographs. I think that he was
Sure.
interested in taking a look at that one more time.
Is this the slide?
Yes. Um, and while we're looking at the slide, if people want to ask more questions, when asked, when we apply the thermal barrier in the battery, does it change the size of the battery, the dimensions?
No, not the specific initial volume of the battery. I mean, what changes the size of the battery, of course, is any swelling that might occur. But typically in battery module installations, there is some tolerance put into the design for the space between the batteries. And so ideally, you'll try to minimize that as much as possible because that will increase the energy density. And so it's ideal to have the thinnest layer possible as your thermal barrier material, but the thermal barrier material should not affect the absolute dimension of the battery cell.
Gotcha. Okay. And also, I realize that people are quite interested in this technology. And you did mention this is development material. When do you expect this to be available for sampling or purchase?
Mhm. So we're happy to sample in the short term. We have quantities of material available to sample to interested OEMs. In terms of commercialization, we're expecting this to be commercial in early 2026, probably in the late spring timeframe of 2026. But we do have quantities available to sample immediately.
Perfect. Okay. Thank you. Um, Muhammadu Guye has asked a question. First, he wanted to thank you for the presentation. Um, he's curious if this material can exceed 1 millimeter in thickness, and well, yeah, more of it is just how to get samples. But I think we just
So
answered that.
good question. So in terms of applications which require more than 1 millimeter, we would likely go to a layering strategy. Because of the nature of the material, it's more challenging to produce at higher thicknesses than 1 millimeter, less challenging to produce at lower thicknesses. So we are working, as I showed, in the test here, this was a 2 millimeter thickness. So this would have been two layers of one laminated together. So we're absolutely happy to have discussions with customers around, their desired thickness and to develop strategies. But I would suggest that it's unlikely that we would produce a monolithic layer greater than 1 millimeter.
Gotcha. And I see some questions coming in from the chat. If you're able to, please do use the Q&A function at the bottom of your screen. That way we're able to properly field the questions here. Another question, Steve. So does this material include PFAS?
No, it's completely non-fluorinated, both in the polymeric matrix as well as in the inorganic filler content. So it's a non-fluorinated material, no PFAS.
Gotcha. Okay. I'm looking at additional questions here. Um, what actually I have a question. So this material is a composite polymer and inorganic combination. Aerogels are typically with some sort of polymer and then some sort of air. What is the weight comparison between GBI and aerogels?
So aerogels are remarkable materials. And to be clear, here at Gore, we are not anti-aerogel whatsoever. We do have some composite materials that do include aerogels, and we think they're fantastic material, for the specific applications. We're a little concerned about using aerogels in the case of battery insulation, as I mentioned, because of the compressibility concerns that they bring. So, the aerogel materials are very light and they're very low thermal conductivity, but when they're deployed specifically to be battery insulation, they're often delivered in the form of a pad, and that pad has some sort of supportive scrim associated with it because aerogels are so light that it would be difficult to just sprinkle aerogel in between, your battery cells. And it's also, a little bit more problematic from a particulation perspective. So I'd say the relevant alternative insulation material is often delivered in the form of some sort of scrim, and the aerogel is adhered to that, and then it's encapsulated as well. And so whereas aerogels are very low density, the alternative materials that need to be deployed typically raise the density of those solutions into the same typical range as Gore battery insulation in that 0.3 to 0.5 gram per cc range. So we're at a comparable density, but remember, weight is not just density, it's how much you're deploying. And so when you can deploy half the thickness of the aerogel pad, that in essence, would be half the weight. And so for those applications that do require very low weight, such as aerospace and defense or even automotive applications, we believe that we can be, a very interesting solution because we can deploy it at a lower thickness of the material with a comparable density.
Awesome. Thank you. Um, I think, give me one moment. There was a question about maximum thinness here. I'm looking through. Um, will you plan to achieve, so this is from William Richardson. Will you plan to achieve a UL V0 rating in the future for this material?
So some of the early investigations we've done have suggested that the UL94HB is sufficient for some of these applications, but we're absolutely interested in getting feedback. And we are a material science company. In fact, many of our products are flame resistant products, and so we have kind of a toolbox of technologies available to us. We're trying to keep the material as simple and keep the cost down as much as possible. But if we hear strong feedback from the industry that something more than UL94HB, if we need V0 for some applications, we're absolutely happy to entertain those discussions.
Awesome. Thank you. And then Bradley Willard asked, how thin can this material be manufactured? I know that your nominal is 1 millimeter, but looking for the minimum there.
That is an area that we really haven't investigated tremendously. I mean, we have produced down to about 500 micron, and in some, really short runs, we've investigated producing sub 500 micron. But again, we're kind of trying to target the sweet spot of the battery ecosystem here. And when we look at prismatic cells for, BESS applications and maybe automotive applications and others, we find that the millimeter range is pretty typical. But again, since we are in development mode here, if you're interested in having a discussion with us around potentially investigating thinner layers, we're absolutely interested in having that conversation. And so don't
Nice.
hesitate to reach out to me on email or on LinkedIn.
Nice. And just as a reminder for everyone, this is development material. And so it sounds like Steve, your team is interested in working with folks, getting feedback and further refining the product before release. Is that correct?
Yeah, I would say that's true. We're absolutely looking for, OEMs and other potential customers who might want to sample, test the material in their application, particularly if it aligns well with some of the applications that we're targeting. It is developmental, but we are in the process of scaling production, and so I wouldn't expect for there to be a dramatic change in the material, but we are interested in hearing feedback, around things such as thicknesses and UL ratings and things like this that might be necessary for specific applications.
Gotcha. Okay. Nicholas has asked a question, Nicholas Hortense. How does the lifetime of GBI compare to aerogels as battery insulation?
Yeah. So, it's challenging to measure lifetime, over the course of 10 or 15 years, of course, but we can do accelerated measurements. We can do high temperature measurements. We expect that based on the chemistry and the morphology of this material, it will maintain resistance up to 800 degrees C. Being as though it's a polymeric composite, we recognize that at 800 degrees C, unlikely to have much polymer left. But the inorganic fillers are what provide the thermal barrier layers. And so that's why we're, for example, in this plot, even at 800 degrees C, we're able to maintain that thermal barrier performance. In terms of lifetime, I'm a chemist and material scientist, and when I think about the materials that are present in the formulation, there's nothing in there that I would expect to age or degrade over the typical 10, 15, 20-year expectation. And so we expect this to be a very durable material over these tens of years of expectation in terms of, at least in terms of the stationary storage market. And we know that the automotive markets and other markets might have other expectations. So I guess the long answer to a short question, but we don't expect for there to be lifetime issues with regard to the chemistry.
Awesome. Thank you. Patricia asked if you can go back to the the contact info slide. Sorry to bounce you
Sure.
around a little bit.
Yeah, no worries. There's the QR codes.
Perfect. I see this is something that's who's asked this? Jonathan Smith asked this question. It was answered as a text, but I also just want to touch upon this live. What's on a lot of people's minds in the US especially is the domestic content and fiat concerns for qualifying for tax credits. I think you mentioned that this material was produced in the US. That's probably the prototyping material. Will the full production also be produced locally?
So first of all, I'll address the fiat. This has absolutely no fiat concerns whatsoever. So absolutely zero concerns around FEOC. With regard to the supply chain, as I showed in the early slides, GORE is a global company. We have a global supply chain. We do recognize the importance of domestic content for the battery industry here in the United States. And so to that end, we have developed our supply chain such that we can deliver country of origin US products of GORE battery insulation. So, we are a global company, but we are, engineering this product and engineering our supply chains to be compliant with the domestic content requirements here in the US.
Gotcha. That's good to know. Thank you. David Dross asked, will this presentation be available in the resources tab website or circulated to participants? We'll answer this first from our side. We're happy to provide the link in our newsletter and also send it out to folks in our post-event email. But Steve, is there any other information you'd like to add?
Yeah, I would just encourage them to get in touch with me directly, and we can provide electronic forms of the presentation.
Great, awesome. Steve, I'm going to actually hold on. I'm gonna just double check questions one more time. Let's see. Oh, let's see. There is a cost question. I'm searching through the questions we've already answered. Let's see. For the cost, Steve, do you have a cost range that you'd be able to quote?
Yeah, I think I'll just refer back to my answer previously, is that we're still scaling and we're still developing the supply chain.
Hmm.
And the costing, will have a variety of different factors, including, the form that the product would be delivered in to that specific customer, as well as the volumes and things. But we recognize that in order for this to be a successful product in this space, that it needs to be cost competitive with materials that are on the market. And so we're targeting, the next best alternative materials and the costing there, and we expect to be very cost competitive and cost comparable.
Gotcha. Okay. Sounds good. So I'm seeing a bunch of questions about Steve's contact information. I'm just going to put Steve's LinkedIn in the chat. So if you want to use that QR code to contact him or reach out to him on LinkedIn, those are a couple options. Yeah, a lot of great interest on testing this material.
Yeah, I'm easy to find on LinkedIn. And I can potentially put into the chat as well my email address if you're not able to use the QR code. I'm just going to type that in right now. So I'm just sending my email address out to everyone.
There we go. Perfect. I think that's all the questions that we have that we're supposed like to answer. So thank you everybody for joining this webinar. Really interesting material, and Steve is also a great lecturer, understandably, and a lot of good fundamentals too. So thanks for joining in on a data-driven approach to thermal installations, and a big thank you for the GORE team for putting this on 2 times at this point. So it's a very well practiced presentation, as you can tell. Yeah, please reach out to Steve if you have any more additional questions. I'm sure that the GORE team will be excited to help you understand a little bit better about the material and how you can get your hands on it. So that's the end of today's program, and we look forward to seeing everyone at the next Volta Foundation event.